For this problem, we are looking at another relativity problem, but this time they are connected A and B. So this velocity is directly related to the velocity of B. And you may be concerned at the beginning because they do not give us the value for r, but because the radius of the circle is connected to the length that they are connected at which, everything ends up canceling out, and it's fine that we don't have it. It's a little bit frustrating because you have to keep r through to the end of the problem, but it works out in the end, so don't worry too much about that. And for here, we are looking for the velocity of A given this angle of 60 degrees when they have given us the value of the velocity of B. Now, where to start? For this problem, we have two triangles that we can make. We can make one where we have A and B connected. And I always like triangles. They help me understand what's going on. And then we have a triangle where there is O and A. Here is A, B, and this is a point that's not given in the figure. And this is A and O, and this is a point that's not given in the figure. This length is R with an angle of 60 degrees, and this length is 2r. And it seems pretty interesting that we are to solve for so much given so little, but let's start taking small steps through it, and as we find more and more information, we'll find out that we actually have everything we need. Starting with the position equations for these two triangles. Let's get that other figure out of the way because it's a little bit more than we need to be thinking about at one time. Pythagorean theorem. OB squared plus OA squared equals AB squared. Let's call this O prime, actually. And this is O. And from this, we can determine that xb minus x of A is that distance, and y of B minus y of A is this distance, and that equals 2r squared, which is AB. And this equation is really nice. It describes that triangle very well. Now let's define this triangle. This is x of A squared plus y of A squared equals r squared. That one's a little bit more simple. You don't have to do any addition or subtraction of vectors. So these equations are nice, but they don't have anything in terms of the velocity of A or the velocity of B, and that's what we need. The best thing to find the velocity of A and the velocity of B is to take the derivative of these two problems. Let's take this derivative first. If we take that first side, we get 2xb minus xa, and multiplied by the inside derivative a dot minus 2yb minus ya times yb dot minus ya dot, and that equals 0 because the 2r squared is constant. That means that it's not changing, and we know immediately that the velocity is 0. And these 2's can be canceled out, and now we just have a pretty equation with dots and no dots. Next, let's take a look at the derivative of this equation. And you have 2xa times xa dot plus 2ya times ya dot equals 0. Once again, we have a radius that is constant, so that will equal 0. This is fantastic. Now we have lots of variables that we can play with, but we need to make a few assumptions on what is given to us. We know that this distance here is going to stay the same. V of B is traveling horizontally, and because of that, we know y of B equals negative r, where this distance is r. we know that it's going to stay constant. Because it's staying constant, we know that y dot b is going to be 0. So when we start solving for x of a and x of a dot, we can put in those values. So let's erase this, clean up some space, and solve for x of a in this problem. We'll get that it is the square root of r squared minus y of a squared, and we'll use this value later. We can also solve for x of a dot here and get y of a times y of a dot over x of a. And once again, we will use that later as well.